All right, so guys, like I was saying, section 3.5, exponential and logarithmic models. We are not going to be focusing on the graphs per se. We're going to show the graphs, hey, this is what it looks like, because I think that's going to help us to have an overall understanding of what it is that we're trying to tackle. But no, in 3.5, we will not ask you to draw a single graph. Again, that we've already done that in chapter 3. We've worked with the graphing back in section 3.2 and 3.1 for the exponentials. But again, we're not going to revisit that in terms of these models. The goals that we have in mind for today, students will be able to use exponential growth, exponential decay, logistic growth functions to model and solve real-world problems. Number 2, students will be able to write an exponential growth or decay model given a set of 2 ordered pairs. I'm going to be honest with you, about 99% of our focus is going to be on that first goal. We're just going to mention or talk about the second, but that's not something that you're going to be tested over. We're going to be testing quite a bit actually next week over goal number 1. So we have 5 what we would consider to be most common types of mathematical models that involve exponential and log functions. But for our purposes, we're going to be focusing on 3 out of these 5. Okay. So again, we have exponential growth, exponential decay, and I would anticipate, quite honestly, that even though maybe we're using slightly different terminology, but we've seen these before, right? You've worked with exponential growth, you've worked with exponential decay. Like I said, maybe you didn't realize it, but exponential growth model, we'd say is y equals a times e to the bx. Well, x almost always represents time, so there's a lot of textbooks out there that you may see to where it actually writes it as y equals a times e to the bt power. X is going to be the time. So again, in some cases, we actually even just write t time. What happens if lowercase a is the quote-unquote principal? Well, didn't that just become the PERT formula? As long as b is the rate? Yeah, so what I'm saying is that you've used the exponential growth model. You used it a lot. Every time you used the PERT formula, you were using it. It was a little hidden, and instead of saying lowercase a and b, we were using capital P for principal and R for rate. That was the only difference, but you've used it multiple times nonetheless. On the 3.1, 3.3 quiz, I think it was number 21. There, it was the equation was built into the problem, but it was talking about depreciation. Like the car was depreciating in value, is becoming less valuable, as time went on. That's the exponential decay model. Okay, so as you look at the difference between exponential growth, exponential decay in terms of the model, there's only one slight difference, and that is that the rate is negative. That's it. That's the only difference. Everything else, it's the same, looks the exact same. But if the rate is negative, then you're not growing in value. You're actually becoming less valuable, or you're not. Your population isn't growing. Your population is decreasing. Those types of things. The Gaussian model, like I said, this is what it looks like. We're not really going to be focusing on that, and it's. And same with the logarithmic models down here. It's not, especially with the log models, those hopefully look extremely familiar. We've worked with those quite a bit. But the reason why we stay away from the Gaussian and the log models here in section 3.5, it's actually not because, this is going to be too complicated and so hard to work with. It's just that it's not very applicable. We're trying to go for real world type stuff. There's a lot of real world examples dealing with exponential growth, exponential decay, and logistic growth. Not a lot that naturally come to be. You're going to notice that we're even going to be stretching the boundaries quite a bit to where all of a sudden we care about the population of fruit flies and stuff. Yeah, I mean, we're going to be stretching this as it goes. We would really have to stretch if we were trying to fit a Gaussian model in there. Okay? The other thing that we could say is that, yes, this is how a word problem is potentially set up to use the Gaussian model, but we could make it into an exponential growth or a logistic growth model, and it would actually make more sense. So again, it's one of those that it's just not very applicable to what we're trying to do. And then that logistic growth model, y equals a over 1 plus b e to the negative rx power. Now here's the good news. You will never be asked to memorize the logistic growth model. In fact, almost always, actually always, for our purposes, the equation will be written into the problem. And it's not going to be even written in like this. It's going to be written in with some of the values already plugged in. Okay, so please don't worry about this as, oh gosh, I have a whole lot of memorization ahead of me. It is potentially going to happen to where you are not given the exponential growth model or exponential decay. We may need to see that one see that one through. But the logistic growth, the new one, so to speak, that is not something that we're expecting you to memorize. So the basic shapes of these graphs, we know what the exponential growth model looks like. We've graphed it. We've worked with it quite a bit. A lot less often we've worked with the graph of the exponential decay, but it probably, hopefully, comes as no surprise. We've graphed a few of these where we had a negative exponent where we're going to be falling. The Gaussian model, often referred to as the bell curve, like I said, we're going to essentially stay away from that, but that is what it would look like. The other one that we're going to be focusing on down here is the logistic growth model. Again, the logistic growth, this is where we have virtually no growth happening whatsoever, and something happens and we skyrocket in terms of growth, but then it levels off. Okay, that's the logistic growth model. That's what we're going to be talking about. And then the others, like I said, with the logarithm and the natural logarithm, we've graphed those. We know what those look like. That's just not going to be our focus here in section 3.5. Okay, so a few examples that we have for exponential growth where we've worked with exponential growth already is with money, but we could also tie this into population growth. Again, in my opinion, as a math person, it's kind of like nails on a chalkboard, but I feel like you hear it all the time where anytime something is growing fast, you'll hear people say, oh, it's growing exponentially. And it's not always growing exponentially. Please understand that it's very possible that something is growing in a linear fashion, but it's growing very quickly. Again, just because something is getting bigger really, really quickly doesn't mean it's an exponential growth model. Oftentimes it's close, but again, not always going to be the case. So again, we're going to talk about population growth quite a bit here. We've already talked about money. We'll continue to do so. Exponential decay, we've already mentioned the depreciation. We've also got carbon dating. I feel like the last couple of years, more and more students have come to class and I say, yeah, it's just like all those carbon dating problems you did in science. And they'll look at me like, what are you talking about? Does that sound familiar to anybody, carbon dating? Working through those? A couple of you guys are shaking your head or nodding your head yes. So again, carbon dating, and again, talk about a gross oversimplification, but basically all living matter has carbon, just how much of it. After something dies and it's decomposing, you can measure how much carbon is remaining. And okay, well, it had 50 years ago it had this much carbon, and now it has this much carbon, and then you can date backwards and figure out how old the thing was. So again, that used to be something that was done in a science class, but it just followed the exponential decay model. And as long as the numbers worked out nicely, it really wasn't that hard to do, depending on what you knew and what you could figure out. All right, so the new one, essentially, though, is the logistic growth model. So again, not getting hung up on this is what the equation looks like. More so trying to wrap our minds around what it is that we're talking about. So again, something that has a minimal to no growth, then something happens and it skyrockets and then it levels off. So again, the world that we all absolutely know now with the spreading of viruses and things like that. Again, that's absolutely the case. I would say that coronavirus, with where we're at right now, I don't know if we can absolutely say that it's completely leveled off. I mean, it's still around. It's not completely gone, but it's definitely not growing at the same rate that it was 2 years ago, year and a half ago, last year. I think actually at this time, were we still in masks last year at this time? Yeah, I can't remember. I feel like we were maybe through the first. I don't know. Not that it matters, but again, that would be a good example because 5 years ago, no one ever heard of the coronavirus. Again, I mean, was it, or very few people had heard of the coronavirus. COVID-19, like that, yeah, that wasn't a thing, right? So we would say that its growth was non-existent. Again, it was not growing. Then all of a sudden, boom, we hit a time, and it skyrockets, and then we kind of figured it out. Okay. Took us a long time to figure it out, and I don't know if we can actually even say that it's completely figured out. But again, it's definitely leveled off in comparison to where it was. All right. We could also talk about the learning curve. Again, if you think about it, I don't know if any of you guys go home and parents ask, well, yeah, what'd you learn today, or something like that. If you were to ask a 4-year-old that same question, again, how many things did they learn throughout a 24-hour stretch? Oh my gosh, it's ridiculous. It's like the whole world is new to them. For you guys, yeah, I mean, I hope you're still learning some things throughout the course of your days. But again, it's you're adding like this much more. Okay, I got a little bit better today. I got a little bit better today. Whereas for a little kid, like they're discovering that I mean, you name it, they're figuring it out, right? iPhone sales, movie attendance, these are all things that could follow that logistic growth model. Okay, I don't know. Think about like a movie. Are there any movies coming out soon that I don't know about? But imagine that there's some movie coming out, say Friday. Well, as of right now, because it hasn't been released yet, that its attendance rate is pretty much non-existent. Again, people are not seeing the movie on Monday, Tuesday, Wednesday, but then Friday night hits, and all of a sudden the attendance skyrockets. After a few weeks, it's no matter how good the movie is, it's going to start to level off. Make sense? Okay, that's what a logistic growth model is going to do. All right, so we are going to actually skip over this problem to handle this one first. Honestly, because the first one that we're skipping over is ridiculous and it's going to take a long time. It's not hard, it just takes a long time. This second one is much more manageable. So we're going to take a look at this second problem in the notes. By the way, does everybody have it? Everybody sees where we're at? Okay, good. So it says the population of a large city in millions can be modeled by y equals 1.8e to the 0.026x, where x equals 0 corresponds to the year 1980. In what year is the population of the city expected to reach 2.5 million? Okay. First off, if you don't have a calculator out, please get one. If you need to borrow one, I've got some up here. But you will most definitely need a calculator to complete these problems. I should have mentioned that at the beginning of the period. So here's where we're at. By the way, I want to kind of translate this, because this for a lot of us might be brand new. X equals 0 corresponds to the year 1980. So our job is to figure out the time, okay? So we might do some work and figure out, and we get, let's just say hypothetically that we get that x is equal to 5. Does that mean that my answer is 5? Because again, if you look at this, we're supposed to answer in what year does this happen? Does it happen in year 5? Well, I mean, that doesn't make sense. No, it doesn't happen in year 5 AD. Like that, no, that's not when it happens, okay? For all intents and purposes, for this problem or in relation to this problem, time starts at 1980. So if we come to the conclusion that the answer is 5 years after 1980, and what year did that happen? 1985. Okay, if we got that x was 15, still baseline of 1980, well, that looks like that's going to be 1980 plus 15. Oh, that's 1995 that would happen. Does that make sense? Okay, so if we have seen this before, then I'm probably boring you with the details. If you have not seen this before, please understand that you're going to start to see this fairly regularly kind of from here on out within a lot of these word problems. Okay? All right, so back to this. We've got the model that's been provided. Just going to rewrite it down here. Y equals 1.8. Now, this is 1.8 million, remember. 1.8 e to the 0.026x. All right, so is this exponential growth or exponential decay? Growth. We know that because we have a positive rate. Okay? If this 0.026 were negative, then we would expect that we were going to be getting smaller. Also, the other giveaway is that we're starting at, well, I guess we don't. We're trying to get to 2.5 million people. Do we understand that this 1.8 represents, in 1980, that's where we're starting? That's the initial population. Okay, if you think, again, just because we've used the PERT formula so many times, that's like our initial principle. Does that make sense? So what's my target? What am I trying to get to? 2.5 million. Do we agree that that is y? That's what we're trying to get to right there. Now, with that one little step, hopefully we also understand the goal is to solve for x. We realize that right now at this moment, that if we just only focused on that equation that we wrote up, that this is just like a problem from yesterday, 3.4. Okay, hopefully we're able to make that connection. Okay, yeah, we know how to solve an equation from here. All right, we have a variable that's an exponent, which means that we need to isolate the exponential. So I'm going to start by dividing the coefficient of 1.8. All right, now here's where we have to immediately begin to be careful. The right side is easy enough. The 1.8's cancel out. We're left with e to the 0.026x. On the left side, that's not going to divide nicely or perfectly, is it? Okay? So the rounding is going to become a deal. So I would encourage you to round as far as you can, Or I would actually even just encourage you to leave this as 2.5